about the synchronous counters. Basically, in this video, we are going to cover the ring counter and the Johnson counter. So these two are synchronous counter. So we already covered the asynchronous counter. Now the basic difference between asynchronous and synchronous counter is that in asynchronous counter we are giving the clock pulse, external clock pulse to only the first flip-flop. All other flip-flops are triggered from the output of the previous stage flip-flops. That means the triggering of flip-flops occurs at different intervals. Now in synchronous counter, we are giving same clock pulse to all the flip-flops. That means the clock pulse will be available at the clock pin of every flip-flop at the same time. So your flip-flop will be working synchronously. That is why the name is synchronous counter. Now first we can see the ring counter. Now ring counter is basically a shift register with a feedback. Shift register is used to shift the data to either to the right or left. Now if you are giving a feedback to the shift register, that will act as the ring counter. Now if you want to design a 4-bit ring counter, you have to use F4 flip-flops. That means if you want to design an n-bit or n-state counter, you have to use n number of flip-flops. So the circuit for the ring counter is shown in the slide. Here we are considering a 4-bit ring counter, and here you can see that we are connecting 4 flip-flops A, B, C and D. Now here we are using D flip-flops. Here you can see we are connecting a single clock pulse to each and every flip-flops. That means the clock signal is available at the same time at clock pin of each and every flip-flops. Now here you can see that the first flip, that is flip-flop A, output is connected to the flip-flop B, and similarly the output of flip-flop B is connected to C, then C is connected to D. Then we are taking the last flip-flop output, that is flip-flop D, and that is connecting as the input of the first flip-flop. So basically these 4 flip-flops will act as the shift registers. Since we are feeding the final output back to the input, it will act as a ring counter. Now here you can see we are giving the reset pin. We already discussed what is the use of this reset pin and or the reset or clear pin and preset pin. So here suppose the data present here, that is the input of the first flip-flop is 1, then when the next clock pulse comes, this 1 will be shifted to this, and here this initially, if you are considering this as 0, that will be shifted, and this will goes on. So before starting the ring counter or before giving the clock pulse, we will clear each and every flip-flops. So when you clear the flip-flops, this output will be 0, this output will be 0, this output will be 0, and this output will be 0. Now here you can see that each and every output is 0, so that means this input, that is the input for the flip-flop A, is again 0. So now if you give the clock pulse, you can see that when the first clock pulse comes, here it is 0. So when it is 0, if you are giving 0 as the input of a D flip-flop, the output, that is next state output, will be 0. If it is 1, next state is 1. So since the input of each and every flip-flop is 0, when you give the clock pulse, the output will be again 0. That means there is no change in the state. Okay. So if you want to get the ring counter, first we will clear each and every flip-flops by using the clear pin. Then we will apply the preset signal to the first flip-flop. So when you give a preset signal, that means when you give a low signal to the preset pin of the first flip-flop, your first output will be 1 and all other output will be 0. Now if you give the clock pulse, you can see that the input of the first flip-flop is 0, second flip-flop is 1, third, fourth again 0. So the output of the first flip-flop will become, this output will become, this will become 0 and this will become 1 because the input is 1, and this output will be again 0 because the input is 0, and this output will become in 0 since this one is 0. Similarly, when the next clock pulse comes, you can see that the flip-flop C input is 1, all other flip-flop input is 0. So the output of C flip-flop will become 1 and all other flip-flop will be 0. That means first case, that is QA, QB, QC and QD. If you are taking first flip-flop, before the first clock pulse comes, this is the output. When the first clock pulse comes, this will be 0, this will be 1 and this will be 0 and this will be 0. And the second clock pulse comes, this will be 0 because QD acts as the input of A flip-flop, and this will be 0 because this acts as the input of this flip-flop. Then this will be 1 because QB will be acting as the input of C flip-flop. Then this will be 0. Similarly, when the next clock pulse comes, this will be 0, this will be 0, this will be 0 and this will be 1. Now similarly, when the next clock pulse comes, this will be 1, 0, 0, 0. That means this will be repeating. So these are the 4 states that you can obtain for the ring counter. So if you are using 4 flip-flops, you will get 4 states only. If you need a 10 states flip-flop, you have to use a 10 flip-flops. So that is the ring counter. So the timing diagram and truth table is again shown here. Here you can see that initially we are making one of the flip-flop as the 1 and all other flip-flop as 0. So here it is shown that we are making QD as 1 initially, and QA, QB, QC is making as 0. And when the next clock pulse comes, your Q output will be 1 and all other output will be 0. This will be 0 and this will be 0 and this will be 0. And similarly, when the next clock pulse comes, since QA is 1, this will become 1 and this will be 0 and all other will be 0. So this will be continuing, and this is the timing diagram for the ring counter. So next is Johnson counter. So Johnson counter, it is just like a ring counter. It is again an application of this shift register. So this Johnson counter is also known as the twisted ring counter. So the working is similar to that of ring counter, but here instead of connecting the Q of the last flip-flop to the input of the first flip-flop, here we are connecting Q bar. We are connecting Q bar as the input of the first flip-flop. Now all other connections remains the same. So just like the previous one, we will be applying a low signal to the this clear pin, so all the output will be 0. So this will be 0, this will be 0, and this will be 0, this will be 0, but Q bar will be 1. So this Q bar is fetting as the input of the first flip-flops. So here there is no need of arranging a preset for the first flip-flop for applying the clock signal, because initially this one is 1. Okay, when the next clock pulse comes, this output, that is the first flip-flop output, will be 1 and all other flip-flop output will be 0. So this will be 0, this will be 0. Again, if you check the input of each flip-flop for the next clock pulse, you can see that this is again 1. That is the flip-flop input for this first flip-flop, the input will remain as 1, and the second input, that is second flip-flop input is again 1. All other flip-flop input is 0. So when the next clock pulse comes, this 1 will be, that is your output of QB will become 1 because the input is 1, and QA is again 1 because the input is 1. Here the input is 0, so the output will be 0. So here the input is 0, so this output will be 0. Again, this is 1, that is this Q bar is 1. So when the next clock pulse comes, again here it is 1, so the output will be 1. Since this is 1, so that is flip-flop B input is 1, so the output will be 1. And here it is 1, so the output will become 1. And here it is 0, so the output of flip-flop will be 0. Now again this one, that is flip-flop Q bar flip-flop 4 will be 1. So again the input of the first flip-flop will be 1. So this will be 1. The second flip-flop input is 1, so this will be 1. This is again 1. This will be 1, and this will be 1. So the final output will be 1. Then it will become 0. So when it is becoming 0 means you will get a 0 as the input of the first flip-flop. So when the next clock pulse apply, your output will become 0. Since this is 1, your output of B flip-flop will be 1. Since this is 1, the flip-flop C flip-flop output will be 1. Again this one, so this will be 1. Now since this one is 1, again this output is 0. So when the next clock pulse comes also, here you will get a 0, and here automatically this one is 0 when the previous clock pulse is coming. So the output of the first flip-flop will 0, then this will become 0, this is 1, this is 1, again it remains. So in the next clock pulse it will be 0, this will be 0, this will be 0, and this will be 1. And when the next clock pulse comes, and all inputs will become 0. That means initially you will be having a state 0 0 0 0, then the output of 1, this is QD, this is QC, and this is QB, and this is QA. So 1 0 0 0, and next clock it will be 1 1 0 0, the next clock 1 1 1 0, next one 1 1 1 1, the next clock it will be 0 1 1 1, then you have 0 0 1 1, then you have 0 0 0 1, then when the next clock pulse comes, it will again jump back to 0 0 0. So if you check here, you can see that 1 2 3 4 5 6 7 8. So total your 8 state will be obtained if you are using 4 flip-flop. So that is just double the number of states that you can get using the ring counter. So in Johnson counter, if you are using 4 flip-flops, you will get 8 states. If you are using n flip-flop, you will get 2n states. So the state diagram and truth table of Johnson counter is shown in the slide. So this is a truth table. This is a state diagram. State diagram means our each states, and its next state is shown as a diagram. Here you can see that the first state is 0 0 0, and the next state is 1 0 0 0. Then next one is this one, next this one, and next this one. And then after this one, it will be continuing. So this is the state diagram for the Johnson counter. Now the timing diagram for the Johnson counter is shown in the slide. Here you can see that initially all the flip-flop output is 0. When the first clock pulse comes, the QA will be 1, and all other output will be 0, because we are feeding this Q3 bar as the input of first flip-flops. So in the next clock comes, this is 1, so this will become 1. This is 0, so this will be 0. This is 0, so this will be 0. And when the next clock pulse comes, this will be 1. So this will be 1. be 1. This one is 1, then this is 0, so 1 will be 0. And similarly, since this is 0, when the next clock pulse comes, this will be 1. Since this one is 1, so this is 1, so this one will be 1. So 1, this will be 1, 1. When this one become 1, that is when Q3 become 1, Q3 bar will be 0. We are feeding this Q3 bar as the input of the first flip-flop, so this will become 0 in the next clock pulse. So here it is 1, so this will be 1, here it is 1, this will be 1, this is 1, this will be 1. Again this is 1, so the input of the first flip-flop is 0, so when the next clock pulse comes also, it will be 0. Then since this is 0, this will be 0. This is 1, so this will be 1, this is 1, so this will be 1. Again this is 1, so the input is 0. This is 0, so this will be 0, this is 0, so this will be 0, this is 1, so this will be 1. So this is how the Johnson counter timing diagram is coming. So these are the two synchronous counter using shift registers, ring counter and Johnson counter. So in ring counter and Johnson counter, we are using the shift register with the feedback. In ring counter, we are feeding the last flip-flop Q output as the input of the first flip-flop, whereas in Johnson counter, we are feeding the Q bar of the last flip-flop as the input of the first flip-flop. And if in ring counter, whatever be the number of the flip-flops you use, the same number of states you will get. That is, if you are using n flip-flop, you will get n states. Whereas in Johnson counter, it will be the double the number of the flip-flops you use. That means if you are using n flip-flops, you will get 2n states. So that's all about it.